Okay. Uh, well, it's my pleasure to introduce Ewelina Zatorska. Ewelina is a professor at the University of Warwick. After getting her PhD in Warsaw, she held postdoc positions at École Polytechnique in Paris and as a Chapman Fellow at Imperial College London. She is interested in partial differential equations, modeling complex fluids. She has authored over 50 publications, which is really impressive at this stage of her mathematical career. She was awarded an early career fellowship by the Engineering and Physical Sciences Research Council of UK, and the title of the fellowship is Non-Local Hydrodynamic Models of Interacting Agents, 2021-2026. This is the most prestigious grant for young researchers in UK, financially equivalent to European Research Council starting grant. So this is really an enormous distinction. Ewelina is also a recipient of the London Mathematical Society Whitehead Prize in Mathematics. She serves on the editorial boards of several respected journals, including the Bulletin and Journal of London Mathematical Society. Okay, Ewelina, the floor, the Zoom is yours, please.
Thank you so much. I wasn't expecting such a detailed CV presentation here, but thank you, first of all, for having me here and in the Baby Steps conference Beyond the Horizon. And thank you, everybody who is in the audience. I can't see you very well, but I appreciate you being there. So a couple of things maybe that I should like to mention to you before I start is that it's actually my second talk during the Beyond the Horizon program within the last couple of weeks. There was another conference within the same program, but I suppose not in collaboration with the organizers in Edinburgh last month. And I presented the slides, almost the same slides, last month, updated by some feedback from the participants. So I'm gonna present it today as well. Also, these are slides that are based on a couple of works that have been actually the main focus of mine during this research program that I embarked on during the last, let's say, 4 or 5 years, really, with a group of people, young people. Some of them actually work in Warsaw nowadays. Some of my former postdocs and PhD students. So the purpose of today's talk is really to draw some directions in analysis of dissipative Aw-Rascle system. I'm going to talk about the results we obtained with colleagues of mine, but also I want to show you and everybody who is interested some open problems, possible research directions for people who have some ideas. And I'll be very happy to hear about these ideas from you today during the Zoom session, but you can also contact me on email if you are interested, and we can discuss it later on. So dissipative Aw-Rascle system is probably a name that I need to explain a little bit. Aw-Rascle system is something that people studying or modeling traffic flow are familiar with, but the name, the adjective dissipative is really kind of mysterious to most, because most of the models of the traffic are not dissipative. There is nothing to dissipate when we describe the motion of traffic. So some key historical remarks. First, all the first idea of describing the traffic using the partial differential equations comes really from Whitfield, Whitman, and Richardson. So we have the so-called LWR model, which is described by one elegant PDE. This is a continuity-like equation. Continuity because there is some continuous quantity, and it is a density rho of vehicles, of cars, on a one-dimensional road that this equation describes. So the quantity that is conserved is integral of this rho. If you use divergence theorem and integrate within on the whole line, or maybe if you have some bounded domain, use some inflow-outflow boundary conditions, you'll see that the mass of whatever this equation describes is conserved. So it's a first order model, and in this first order model, the velocity of the vehicles, v of rho, is given. It's a function of density, usually a decreasing function of the density, which means that if this function hits zero, there is no motion, there is no velocity, which means that your cars are stuck in the traffic jam. This is what this equation roughly describes. But it's been, well, despite its popularity, and it's surprisingly captures very well the traffic flow on one-dimensional road when no other interactions between the drivers is possible, rather than just following car ahead of you. This model has many drawbacks, and the drawback is that the velocity is so simple function of the density. So as a resolution of this model, Payne and Witham, but also consecutively O and Rascal and Zhang, proposed to consider the second order models. So in this second order models of traffic, the velocity u is not a given function anymore. It satisfies some PDE, and this is not very clear here because I added another PDE that describes some evolution of velocity vector field W here instead of u. So W and u are two different velocities. One is the actual velocity of motion, u, and w is the preferred or desired velocity of motion. Yeah? And those velocities are now connected with additional algebraic relationship. So there is no more PDE, just one more for w, and algebraic relationship for w and u. And what does this algebraic relationship say? So it says, so first of all, P of rho is some sort of positive or non-negative function of the density. Okay, so this quantity is positive. Yeah, so this means that my actual velocity of motion is always smaller than preferred velocity of motion by the offset of the velocity P of rho, which is function depending on the density. So again, the idea is very similar. I travel with some velocity u, and I have some desired velocity w, which would be, I don't know, if I was on the highway without any speed restrictions, it would be infinity, right? But on our highways, well, I don't know what the speed limit on Polish highway is anyway. But in the UK, where I live right now, it's 110 miles per hour. Yeah, this desired velocity. But I cannot travel with this velocity that much because there is congestion. So this function of P of rho damps my actual velocity of motion, and I travel slower. Anyway, Orozco and Zhang proposed that this desired velocity of motion should be described by another, what we call conservation law. So equation that looks the same as the previous equation. So there is some transport velocity u exactly the same as in the previous equation, but the transported quantity is rho times w. So it's a momentum associated with the desired velocity of motion w, yeah? And rho times w, so mass times velocity is the momentum when we look at this equation, yeah?
So just a very basic question, if I could. So the first model is a partial differential equation. There is one function which we would like to find, and for the second model, there are in fact three functions, but only two differential equations and one algebraic equation. So in fact, it boils down to
finding two unknown
functions. Yes.
Mm-hmm.
Okay.
True.
Thank you.
Yeah, and we'll come back to this later on as well. So indeed, what I present right now is this kind of system of two conservation equations and algebraic closure. And of course, if I plug in this algebraic closure, it is very simple here. It's explicit, right? To the momentum equation here, I can write everything in terms of u and look only for rho and u as unknowns, or I can use w as an unknown and plug in for u here and obtain the equations for rho and w. Yeah, that's how it works. So indeed, we'll be talking about models like that. And just another historical remark, I don't have the names on the slides, but it's very easy to find. There is initially, when this model was proposed, P of rho was something like rho to power gamma. And it mimics really the pressure in gases. That's why some people call it a pressure function. Yeah, rho to power gamma, which is like barotropic pressure. For those of you who work with Euler or Navier-Stokes equations, it's very familiar object to see. And immediately after this model was proposed with this rho to power gamma offset function, it was criticized. And one of the papers that criticized it was called Requiem of hydrodynamic models of traffic equations. And then immediately people tried to fix this error in the model. So this kind of function causes that interactions between the agents that this model describes are like between particles of gas, which is not right. When we are in the traffic, even if it's one-lane traffic, we should mostly interact with agents ahead of us, right? We should mostly respond to what drivers ahead of us doing, not so much to the backward waves, what we say. And there are some fixes possible to propose when this function is something more complex. I'm going to talk about it later. But I really like it that there was this kind of discussion even in the titles of the papers captured. So first paper was Requiem for these models, and the second paper was entitled, of course, if we have Requiem, then we have to have a resurrection. So there was a resurrection of second order model for traffic, and you can see the references in the literature. So, but this is not what I am very interested in, the 1D traffic equations. What I was interested in, and what I set up to do really when I came for my second sort of postdoc, and it was in the UK, was to understand what happens in multidimensional setting. Yeah, and if you think, I'm going to draw a little picture here. If you think about what one-dimensional traffic models do, is they talk about how cars should interact with each other when they travel in one dimension, in one line, and they observe maybe only cars ahead of the car that I'm at. Yeah? If I'm this driver, I notice what this driver does. I maybe adjust my velocity and position to the velocity and position of this car ahead of me. Yeah? In multi-D, the situation may change, right? Because let's say that I'm this driver and I have two lanes. There are some cars here or some other vehicles, right? There is maybe some car ahead of me. It's not clear anymore whether I should only look at car ahead of me when I drive my vehicle, or maybe car on the next line, or maybe somebody next to me, or maybe even I should look at the rear mirror and check what cars behind of me do. I mean, I, for example, don't like when somebody is driving bumper to bumper with me, and I try to avoid situation like that. I try to move to the slower line. So of course there is some backward interaction, yeah? And I'm not trying to put on my modeler hat right now and convince you that I am very much into modeling, because I'm not. But if for a moment we accept the idea that this sort of behavior, this sort of interaction between individuals should be again described by the two equations, conservation of continuity of mass and of some kind of not very well precise momentum that is described by W in multidimensional setting, this will be my point of departure, okay? So I want to study models like that I have to look for density and some velocity W, and maybe there is some function that relates my U and W in some way, okay? There will be some closure for the system in order to have the same number of equations and unknowns. Okay, so this is the idea that was proposed to me really by somebody who is much more into modeling, as I said. At that time, when I was working at Imperial College London, Pierre de Gond was there and his whole group working on pedestrians and bacteria and all sorts of interactive systems. And I really liked, well, I wanted to analyze those models. So in case you want to cook up this closure relationship, if you remember here, we had the following relationship, plus P of rho, right? And now P of rho was some function of the density. I said it could be rho to power gamma. So if I now move this model to the multidimensional world, there is some mismatch of dimension, right? Because W is a velocity vector field and it's a vector field. There's another vector field and now I have to compare with them the scalar, right? So in multi-D, there is of course this abstraction number one. And in case if we replace this scalar with vector of scalars, so P of rho is equal to P1 of rho, P2 of rho, some given functions of the density in multidimensional setting, this model and links of this model with the so-called follow the leader macroscopic model of traffic and really design of the right closure relationship based on data is something that you can find in the paper of Michele Harti, Mutari and Visconti from 2018. And since then, this was the first paper that they proposed. And since then, they are improving this results in the context of the two-lane traffic. So really two-lane highway traffic. So again, I'm not really presenting you the up-to-date results on that. If you are interested, it's enough to put this paper on Google Scholar and see how many people are citing it, how many improvements are built on that one publication. Yeah.
Sorry, so this
How many? How many?
Many, many, many. I stopped at some point.
Roughly, so 200 citations or what?
More,
More.
more. And like,
1,000?
whenever I get the paper as an editor, Michael would be my to-go person to give me a quick opinion about, whether the update is significant or not. A lot of people refer to this paper now. Yeah.
sorry, so
Actually, yeah, sorry.
the square bracket indicates the presence of a vector, yes?
Yes, it's a vector. It's a
It's
two-dimensional.
two-dimensional, yes?
Yes. Here, for the two in this paper, it's a two-dimensional vector. Yeah.
Okay, thank you.
So now let's finally discover what this dissipative Aw-Rascle system means. So for me, what I'm going to focus on is situation when this mismatch of dimension is solved in the following way. So instead of having a vector of some scalars, I will have a gradient of some scalar function P of rho, okay? And I'm not interested in any function P of rho. I'm interested in particular function of P of rho. So this function P of rho, maybe it's not very fortunate how it is written. It tells you that I have some increase of density, but I have also some maximum value of the density here. So my P of rho is increasing function of the density, but it can reach some maximal value of the density, which is denoted by rho max. Yeah, it's also a function that disappears when rho is equal to 0. And I need to, well, multiply any of such function by some parameter epsilon. Yeah. And this parameter epsilon tells me how fast, I would say, this function explodes close to rho max, okay? How sharp the explosion is here. So once again, my velocities are connected by gradient of some function, and the dissipation really comes from the fact that if I plug in this function to the continuity equation, I'll see some dissipative effect. We'll come back to that. But
Sorry,
the
I'm a little
other,
bit worried about this exponent gamma. So it is a specific number, or you consider the family of models parameterized by this
it is
gamma?
a very good question. For now, let's fix it. For now, it will be fixed, and it can be something positive. Gamma is positive, okay? So let's say let's say it's 1 for the moment, yeah? What tells you that it's some sort of family and that I am going to look at some limit process is parameter epsilon in this equation. But I will come back to a couple of what we called heart congestion limit problems later on in my slides. So just to go...
Excuse me, one more question. So usually in such cases, people interested in modeling such situations postulate this kind of function, but then this parameter is somehow extracted from what? From observations, experiment, or?
Many things. So yes, so sometimes it works like that. Mathematicians cover with their theory or like numerical approximations some range of gammas, right? And then they try to tailor these gammas to what they see in experiments. There are various experiments that mathematicians can do in our mathematical labs. What I like, and I don't have it with me, are Lego little Lego robots that have that you can put in like a container and see how they interact with each other, how the traffics are or concentrations happen, and try to numerically adjust this parameter gamma to that. But the group of people in Aachen really they really read data from the highways nowadays, and the offset function is far away from being that simple. Even a vector of such functions is something that is not suitable for describing interactions on the highway. So their functions here, I wrote it here in a shy way, that there will be maybe some implicit function, maybe there will be some noise element in there. It can be really, really much more complex function than what I'm presenting today. So today we're gonna do the...
Model, yes?
Yeah, this is an absolutely toy model.
Okay.
But this toy model was investigated really recently by Pierre de Gond and his group that I already mentioned. So it's not actually so recently, in 2024, they put a paper where they analyzed this model in context of pedestrian motion. Okay, so they checked that this model and numerical simulation satisfy something that is called fundamental diagram for the pedestrian models. So sort of they verified that it is a valid model for how pedestrians, without any obstructions, without any interactions other than between themselves, move. Yeah. So if you wish, it's not the right model maybe for traffic because of these backward ways that I mentioned, but it is indeed a model of some other interaction, and the interactive agents should be people. Okay, so this talk is going to be focused solely on analysis, and I will be switching my domains, switching the unknowns. As you see, we have one equation which is sort of loose. But let me discuss connection to this of this model, of this pedestrian model, as we now hope it should be, to another famous model that my colleagues in France are very interested in. So if you rewrite the Dissipative Aw-Rascle model again in 1D, so this is what it says: have continuity equation in 1 dimension, momentum equation in 1 dimension, and velocities are connected by a gradient of some function of the density. It's a bit weird thing to do, right? Because I moved from 1D to multi-D. I said I justify this gradient being here because I'm in multi-D, and now let's move back to 1D. Indeed, I want to do it for some reason. Okay, so if I do this and I rewrite the equations in terms of rho and u only, it turns out that I can come up with some function lambda rho, which depends on the offset function p of rho. Yeah. And if this lambda of rho is of that form, the model that I end up with, yeah, provided all these operations are justified, yeah, and they are justified only if everything is smooth, which it will not be the case usually. So this is an effective model of motion of some rigid spheres immersed in some lubricant. Yeah. So what I say is that if you put three-dimensional balls or just spheres in one-dimensional domain and surround these spheres with lubricant, and the spheres can only move in one-dimensional domain. Yeah, and now if you make the spheres of equal radius, which is epsilon in that case, yeah, and try to imagine what happens if you try to zoom out now from your domain and see it from the very far distance. So you see more and more and more and more spheres. They become smaller. They still have size epsilon, but they are becoming smaller in your zoom out picture. Then you obtain this model, which is called the macroscopic model from the microscopic description. It's a whole derivation, and of course I don't have time to present it. But in this macroscopic model, the function lambda of rho is something that we call viscosity, yeah, and it is a viscosity of the lubricant of the intestinal fluid, and this viscosity goes to infinity when rho goes to 1. So my rho max is 1, explicitly given here, okay? And it means that the lubrication prevents really collisions between the spheres, okay? So if the spheres are of density 1, yeah, the maximal packing of the spheres is when density is equal to 1 everywhere. And lubrication forces, so the dissipative lubrication forces, prevent contacts between spheres to happen, even in the macroscopic level, yeah? Even in the macroscopic level. And this lubrication force is somehow proportional to the size of our beads, yeah? And if they disappear, this lubrication force should also disappear, at least in the region where they don't contact each other, yeah? So if you imagine the spheres shrinking, there's more and more lubricant around them, spheres are smaller, and the lubricant sort of don't see the spheres anymore. And we have just compressible, what we call Navier-Stokes equations describing this flow.
Sorry, I'm a little bit worried about the units after seeing this expression 1 minus rho. So rho is dimensionless, or?
Yeah, you can rescale this equation. So 1 is just some maximal density after rescaling, yeah?
Okay.
So we assume in this microscopic model that the density of the spheres of the balls is equal to 1 in that model, okay? And that's why we have 1 here. But of course, to study all the interesting limits, you always need to divide velocity, density by the characteristic values, and only then you can say something about asymptotic behavior of the quantities.
So there is some normalization.
There is some normalization here, yeah?
Okay, thank you.
Okay. I'm quite aware of time, and we talk about modeling. I talk about modeling much more than I would like to. Let's try to slowly diffuse into mathematics, maybe. So let's make some observations about the multidimensional model. Yeah, the modeling part is over. Let's try to see what would be even the framework for us to try to analyze these PDEs. So I'm back with my multidimensional dissipative Aw-Rascle system. I'm not dragging along this relationship between U and W, but it is here somewhere, okay? It will be given at some point. But now I have the two following reformulations of that system. Again, provided that all quantities are smooth and I can differentiate them, yeah, or integrate equations and so on and so forth. So now if I plug in, if I try to get rid of velocity from this equation, of the velocity U, and I plug in for W, I see that this equation changes into something that is, well, not so neat anymore. So I have some continuity equation with the right-hand side, which is a bit worrying because it looks like a second order derivative with respect to the density. But I also have this very nice structure in the continuity equation. So if P is some increasing function of rho, this looks more or less like heat equation or the fast diffusion equation or the porous medium equation. So there is some dissipative component in the equation, and it's described by this function P of rho. Yeah. So that's why dissipative Aw-Rascle system. If on the other hand, I want to do what I did in 1D, right? And write this system again in terms of density and actual velocity of motion, I see that it really resembles Navier-Stokes equation. So I have this density-dependent viscosity. somehow related only to the bulk what we call bulk viscosity, so the volume viscosity of the fluid. But then there is some commutator term on the right-hand side, which might be unpleasant to deal with. Because if you write it like that, it kind of involves second-order derivatives again. And in PDEs, the more derivatives that you have, the more unpleasant things may get, especially if derivatives are mixed with nonlinearities. And P of rho, in general, is nonlinear function of the density. Okay? But if you, again, look at this equation and plug in one-dimensional vector fields, you'll see that this commutator vanishes in 1D. So there is nothing like that, and we are back to our Navier-Stokes type of equations in 1D. Yeah. So these are just observations for people who are familiar with Navier-Stokes equations or Euler equations to see where we might be. Okay, we are close to Navier-Stokes equations, but it's a pressureless Navier-Stokes equation. There is no pressure in these equations. There is letter P, but it denotes something different in this model. Yeah. But also we have some surprising regularization effect happening for the density. This is very unusual for Euler or Navier-Stokes equations. Yeah. One more remark is that if you choose to use this offset function in kind of more elaborate way, if you describe it by some kind of non-local operator, so there is some kernel K which convolves density rho. It doesn't have to convolve the density rho, it can convolve other quantities in the system, but this is the simplest way. This system, dissipative Aw-Rascle system, is linked to something that many people also in Warsaw are interested in, which is called Euler alignment system. So why is it Euler alignment system? First of all, there is no evident dissipation in these equations. There's conservation of mass, conservation of momentum, and there is some funny operator on the right-hand side. And this operator is a macroscopic version of the Cooker's-Mail equations, famous microscopic Cooker's-Mail equations, which tells you how velocities of agents that interact with each other align with each other. So these sort of models are used to describe swarming, so the creation of these beautiful patterns between birds or bacteria or mammals and so on. It's the so-called Euler alignment model. So we are kind of zooming out. We want to cover as maximal class of P of rows as possible and have some analysis for models that are widely used in description of any collective behavior phenomena, really. So in this model, the so-called communication weight is a Hessian of my offset kernel K. Now, in the interest of time, I will probably stop drawing more parallels with other two-velocity models that people are interested in the community. I'm not sure if there is anybody interested in SPDEs in this group of people, but if you are, there's a very interesting series of papers by Daryl Holm from Kamasa-Holm equation, and also Flandoli and the whole French-German group working on models where the two velocities are connected by the noise. It doesn't have to be Stratanovich noise, Stratanovich integral. In some cases, it is interesting to consider perturbation by the noise in the transport velocities, and we've studied also fluid equations together with my collaborators, Bright, Hoffmanova, and Feiereisel in 2022 with offset like that. But today will be completely deterministic.
Is this two-dimensional? Is this in 2 dimensions or just multi-dimensional?
So yeah, the advantage of dissipative Aw-Rascle is that you can consider as many dimensions as you want. This series of works are usually in 2 or 3 dimensional setting.
Okay.
Yeah.
And what is the meaning of this Q in this expression?
It's just so it can be some function. It can be depending on what people can cover. It can depend on the momentum. It can depend on the density. It's given.
Okay,
So it's a
I
string.
was a little bit worried by your font. This is Blackboard Q. So.
No, no. No, of course. So this is 2D, 3D. There are some models which don't really make sense in 3D, which work with notion of rotation. Yeah, and we have to be careful what we call rotation of the vector field in 3D, but it's usually multidimensional. Yeah, as people working with fluids, 2 and 3D are usually our go-to problems. So now what is our goal? I have two goals in mind and two problems that I would like to explain you how to solve. First, I would like to understand how to prove existence of solutions to the dissipative Aw-Rascle system in multi-D. And I want to focus on particular solutions. So I want them to be global in time. So I don't want to make any restriction that the time has to be very short. Yeah. And I don't want to restrict the size of initial data. So there is no smallness, neither on the data nor on the time of existence of solutions. So this is problem number one. Second problem that I would like to consider is the following problem, which we called hard congestion model, hard congestion problem, or hard congestion analysis. So if I take my offset function of this form with my maximum density being prescribed to 1, let's say I take some general alpha beta positive. Yeah, I want to understand what happens when parameter epsilon goes to 0. What happens with this model? Yeah, so when parameter epsilon, oh, forgive my drawing, should have taken bigger tablet, but I was cycling to work and bigger tablet is bigger load. So what happens when parameter epsilon goes to 0 here? This part of diagram becomes almost invisible, and but the blow up still happens at my value rho equal to 1, right? So parameter epsilon tells me how steep, how fast the blow up is around maximum value. And surprisingly, it corresponds to, there was a question from the audience before, so I'm going to put it here. It is really the same limit as the limit on the left-hand side, as the limit here. So I can also try to approach the singular value from the other side, right? I can draw rho to power gamma like that. And if I take gamma being bigger and bigger and bigger, I approach the singularity from the right-hand side. So I have blow up, but from the right-hand side, yeah, in my model. So I'm interested in limits like that. What happens if this function becomes singular around some value? And why am I interested in it? Because it tells me, okay, if this function becomes singular and maybe negligible in the region when rho is strictly less than 1, then there is sort of no interaction between the agents. And they are only interacting with each other when they are very close to congestion. And this is what we see in many collective model problems, that when the agents are far away from each other, they sort of don't pay attention to each other. They only try to align their velocities or avoid collisions when they see, okay, now I'm really close to somebody who is moving towards me. I better avoid it, right? I better avoid collision. So these are the
Is P and P bar the same here? Because we have P and P bar.
Nah. No. So what happens if I consider any of these limits? So let me erase it so that we can see the system clearly. So I hypothesize, at the moment it will be hypothesis, and I will try to prove it later, that when rho, when I take gamma n going to infinity and the offset is given like that, or if I take epsilon going to 0 and the offset is given like that, I end up with a model like this. And now what is the unknown in the model? So I have, again, continuity equation and the momentum equation, they look exactly the same. But now I have the following switching relationship between the quantities. So P bar is another unknown. So P bar is limit in some sense when, sorry, I switched the slides. When epsilon, let's say that we use the right-hand side model. When epsilon goes to 0 of P epsilon of rho. This is some limit. It might be something awful. It might not even be a function. It might be a probability measure, yeah? So my unknowns right now are rho, W, U, and P bar. So I have 4 equations, 1, 2, 3, 4. And what the system tells me is that 1 minus rho times p bar is equal to 0. So if it happens that rho is below this critical value 1, right? If this bracket is positive, then p bar automatically has to be equal to 0. So it really is something that kicks into your model when rho is equal to 1. Okay, so it's a measure that concentrates only on the full congestion, yeah? And it is something that is supported on the region where the full congestion happens. Okay, so I hypothesize that I can recover a model like that when
So the
W
gradient is meant in the distributional sense, yes?
if yes, yeah. So if I have a chance to speak about functions, this will be meant in the distributional sense, but sometimes I will move to measures. And then I have to talk about something that we call dual solutions. I have it at the end of my slides, but I see that it's very unlikely that I'm going to cover that much. So, but this is very good observation. This will be something extremely singular. Maybe, you see, if the support of function rho is very irregular, this might be singular on some very irregular topologically set, and then the problem begins. Yeah, how to analyze this set? What is the boundary of it? Does it have a boundary of any Hausdorff dimension? And many, many interesting questions. Okay, so I showed you 2 problems. Let's look at some solutions, shall we? So we start from multidimensional dissipative Aw-Rascle system. And I made a refresher here. So what I assume is that P of rho is some rho to power gamma. For the moment, no singular limits, nothing. I just want to understand what sort of solutions I should be working with. So rho to power gamma with some gamma positive. Yeah, the simplest function I can imagine. I want to work with it and see if I can have some solutions. So I supplement the system with initial data and its density, which should be non-negative, and initial momentum in terms of rho times W. Yeah, if I have that, this function P, I can recover the momentum for other velocity. And now, what we like about the system is that it comes from physics. So certain quantities should be conserved, or at least should not increase. So we define the energy, the initial energy, and unlike in fluids, it considers some interactions, but they don't come from the sort of potential source, if you wish. They come from elastic source, let's say. So there is kinetic energy that is just mass times velocity to power 2, right? And then there is this kind of porous medium energy, if you wish, that comes from the dissipation in the continuity equation. And it is described, it's just calculated in your system as the integral of P of rho. So a prime of P of rho, yeah? Primitive, sorry, not prime, primitive of P of rho. So somehow I was lucky and I defined this energy. Let's see what estimates I can get, yeah, for this energy. For that, I'm going to rewrite the equations once again using some new unknowns. And now I'm going to rescale my nonlinearity a little bit. So I introduce function Q of rho, which is related to P of rho. So again, okay, P of rho is some power rho to power gamma. So Q of rho will be roughly the same power of gamma minus, sorry, plus 1/2 power, yeah, because I multiply by rho, square root of rho. Yeah, but from here, you see that if I multiply this equation, continuity equation, by P prime of rho, integrate by parts, I can get some a priori estimates. And also from this equation here, if everything is smooth, if I multiply this by W, integrate by parts, it's just a advected quantity. Yeah, rho times W is conserved, so I will have some conservation of energy coming from this and coming from that equation, but not from the transport, but from the dissipation, which is here. So this a priori estimates can be summarized as follows, yeah? Having this initial data in energy bounded class, I have the following a priori estimates, so some estimates that work provided that everything is smooth in my system. And I choose to write it not for a particular solution, row W, but for the whole sequence of solutions. Let's say that I was very lucky and I constructed the whole sequence of solutions. I denoted row n, wn. So this sort of estimates, a priori estimates, are uniform with respect to parameter n. So if my initial data is bounded uniformly with respect to parameter n, so are these norms. Bounded in the Bochner spaces L infinity, LP, LQ type. And for some quantities, nonlinear functions of the density, I even control some gradient. All this analysis, I should mention, is done on d-dimensional torus. So D is my domain, omega, and D is either 2 or 3. So very simple model, toy model, as one of you said.
Sorry, just a quick question. The W12 is presumably is a Sobolev space, but this first index is related to the derivatives, and the second is just Hilbert, yes?
Yeah, H1. So this is H1 space.
H1. Yeah. Okay, thank you.
Right? So first index is always integrability with respect to time. Second index is the spatial. Some people write x's here and time here. Sometimes we do, not at the moment. Okay. So let's look at this a priori estimates and let's see what they give us. So first of all, some red flags. There is no uniform bound on velocity w or wn. So everything that I have here, it's just one estimate I wrote at the moment, is multiplied by rho n. Yeah, and I was always highlighting it that my functions disappear when rho is equal to 0. And in the end, if you look at the equations, everywhere in this equation you have some factor of rho n or square root of rho n. So when rho n disappears, when we reach something that is called vacuum, mathematical vacuum at least, yeah, then this system has no, you cannot solve for w with rho being equal to 0. So w is not even defined independently of density. Yeah? So probably rho and w are not good candidates for solution. I should maybe talk about rho and some coefficient. Let's say maybe this is the best candidate for my solution. Yeah? And maybe I should always consider w with some weight that depends on density. Second observation is actually something very positive, is that the estimates for rho n, sequence rho n, are actually pretty strong. As you notice, there is some Sobolev regularity to be had for the sequence approximating the density. And also I know that the continuity satisfies the momentum, continuity, that the density satisfies continuity equation. So there is a hope to have bound for the time derivative of the density, at least in the sense of distributions. Yeah, if I test it by some smooth function, integrate by parts, with the a priori estimates that I have a chance to have those quantities bounded in the sense of distributions. So something like a generalized Oben-Lyon's lemma could work to show that a sequence approximating density, so rho n, converges strongly to the limit, which is great. Because if you want to compose it with non-linearities, this will help you a lot, yeah, in the system. So now, looking at this a priori estimates, let's look at the equations and see. Let's try to ask ourselves a fundamental problem. If I constructed solutions, sequence of solutions that have this a priori bounds, 1, 2, 3, could I show that the limit when n goes to infinity of the sequences generates some rho and w multiplied or not by another rho, such that this pair satisfies again, in some sense, these two continuity equations, these two conservation equations. This is the so-called topological stability argument, and it is a key in every analysis of nonlinear PDE, okay? If I have sequences, can I show that there is some compactness argument that allows me to A, find the limit, B, show that the limit satisfies again the same system in some sense, maybe weak, maybe even weaker, yeah? So for this, I look at my a priori estimates and I see that they allow me to estimate the fluxes in the continuity equation in something like L infinity LP, L2 LP, with P larger than 1, something related to the powers that I have here. So this is not too bad. I can still think of some Lebesgue or Sobolev formulation for that moment, for that continuity equation, yeah? The problem appears here. If I look at the momentum equation, it turns out that the fluxes here are uniformly bounded only in L1. So the most I can extract from my a priori estimates are uniform L1 estimates. And we know that L1 is really bad. Why? Because if I have a sequence in L1 uniformly bounded, it is not true that the limit, if I select a subsequence, stays in L1. Yeah, L1 is this critical space where concentration can occur, and this is actually used to generate some measures. Yeah, so let me tell you about the idea of solution that we need to start from because of this bad uniform estimates that we have. So there is recent trend in analysis of hyperbolic conservation laws to try to identify the solutions through the so-called Young measures. And Young measure is just a measurable map, so that allows you to map points of some domain in RK. It's a mapping that takes a point and associates to it a probability measure on Rn. Yeah, just let's think about this mapping. So it is in the sense that for any test function from C0 Rn, yeah, this mapping is described by the integral. I take any test function. Xi is something, if you are familiar with Young measures, that I would sometimes quote a dummy variable. So it's a parametrized family, and the parameter is z, and z runs in Q. Yeah? Okay, so any measurable function u, ignore the index n at the moment, from Q to Rn generates some measure. Yeah, let's introduce these Young measures. It generates some measure because I can center a direct measure on my u of z. Yeah, so this is actually a good probability measure. It's atomic measure. Yeah, so for free I have this quantity, and now a Young measure is going to be a limit of measures like that. So a Young measure associated or generated by a sequence un is a limit of, so this is a bit of abuse of notation. I'm not talking about function un, but about this measure generated by my function un. Yeah. So a limit of such measures in the usual topology for the measures. Yeah. So weak star limit for any test function generates something, we call it capital nu, and this is the so-called Young measure generated by the whole sequence un. Yeah.
Sorry, I'm a little bit confused since you wrote weakly star, and also this is quantified over G belonging to C0, but the pre-dual of L infinity is L1, so it's the same, or?
No. So this is weakly star in this sense, yeah? That's a convergence in weakly star. But the bracket is understood for, these are two objects. Yeah, the bracket, this action is understood for all G functions.
Yes.
Yeah.
Yes. What I have in mind is the following. In general,
This is not a dual of anything. It's not. These are not dual. These are not dual to anything. Yeah.
Yes, but why using this terminology of weak star?
Because this object is still parameterized with z. Okay, and I have weak star topology on the domain where z lives. Okay.
Okay, so Q is different from Rn. Q is
Yes. So now I know it's very
okay,
confusing.
I see.
It's always super confusing to my students when I explain it to them, because I say something about L1 sequences and then generating the measure. Yeah, this is not a measure. This is not a measure on the space where your function lives. It's a measure that is generated on the space of values of your function. Okay.
I see. So I showed some confusion, but now it's clear. Thank you.
So now
for any z, you have measure nu z, yes? Or vz, or how do you?
Yes. Yeah. So I was try to give you some intuition, but And unfortunately, I don't have many examples here. So what this measure is, so when you think about weak solution, I don't know who in the audience is familiar with weak solution, but weak solution is telling you something about average solution. So you test your equation by some test function, which tells you like I microscope on some region around some point, and I can tell something in average how my PDE is satisfied, right? This is what the weak solution does. And now we zoom out from that description and we probably have even weaker solution, which is described by this Young measure. And this Young measure tells you what is the probability that I have weak solution of that sort? What is the probability that I have this formulation, this distributional formulation, yeah? So if it happens that your Young measure is a Dirac delta and you have probability equal 1 exactly when this weak formulation happens, you have distributional solution. So it's another level of weakening the definition of the distributional solution. Yeah. In a sense, you get this kind of, you can always have some probability, be it 0, of having some distributional formulation, right? So in a sense, you get this existence of Young measure solutions for free for any PDE. But if you are able to prove something about this probability distribution, you gain again some knowledge about the PDE. At least this is how I understand it and how I like to think about it, yeah?
So what is this function B? How it is defined? Is a function on what?
B here. So now about Young measures, a word about Young measures, about oscillations and concentrations. So if it happens that your sequence that you start from, sequence of functions, is uniformly bounded in L1, and you have some nonlinearity, some function B of UN bounded in some LP with P bigger than 1, which means that you kind of exclude the concentrations, then Young measure is a very convenient way of expressing limits of such objects. So compositions of weakly converging sequences with nonlinearities is something that the Young measure is tailored to do. You have elegant formula that tells you what your limit is if you have this property. But if your nonlinearity composed with the sequence, maybe only weakly converging sequence, is just L1 integrable, you know that there might be some concentration, right? Because of this L1 boundedness here. So in our system, we have only L1 boundedness and might be some concentration in the system. So then, okay, you can still say that B of UN converges to something, but this something might be only a measure, right? It might concentrate. And this is what Young measures are not capable of doing. So what we introduce is some sort of defect of the measure, or offset of the measure again. But I think I use offset in other part of the talk, so maybe let's call it defect of the measure. So you have nonlinearity can be to some extent, to some error of the measure described by the Young measure.
Okay, so this B is just some function.
Nonlinearity, just some nonlinearity. It can be something to power 2, usually in the...
Yes, but it's scalar valued, yes? It takes a function and spits out a number, yes?
Yeah, B of...
Okay, thank you.
So just a nonlinear function in general, yeah? And now our definition of solution is like that. So my solution,
We need to approach conclusion.
Yes, I will approach a conclusion on the next slide.
Please.
On the next slide, yeah? So our definition of solution is therefore the following one. I take my sequences and they generate some Young measure. So this Young measure lives on the phase field generated by values of these 3 sequences. And my solution is Young measure like that. It is parameterized with time and x, yeah? So my z lives here. And I identify density by integrating this Young measure against the first dummy variable, and Q of rho is identified by integration with respect to the nonlinearity applied to this dummy variable. And then I can do the same with the gradient. What you can show is because my sequence of densities converges strongly to the limit, your Young measure actually disintegrates to some delta centered on rho, yeah, and another Young measure that is generated by this sequence, more or less, by this sequence and that sequence, yeah. And my solution is this Young measure plus 3 offsets, plus 1, 2, 3 defects of the measure. So actually what I am telling you is that I can find a solution like that in the sense of distributions, which is some Young measure and additional 3 unknowns. But these 3 unknowns are compatible in some sense. So this means that if it happens that one of these offsets in the energy inequality is equal to 0, yeah, then the 2 other ones that appear in the continuity equation and energy inequality are also equal to 0. Yeah, this is what it says, compatibility. And that's something that we use to prove our first result. And unfortunately, I'm going to talk only about our first result, which says the following thing. First of all, there exists a measured valued solution to the dissipative Aw-Rascle system in this multidimensional setting. Yeah, this is what I said. We can prove it. We can approximate the system. We can generate the sequences. We can pass to the limit, get the Young measure associated with the limit. But it says also something more. I said to you that this is almost for free, yeah, to generate some probability distribution. But it says more, like assume for the moment that we have a strong solution to the dissipative Aw-Rascle system with the same initial data. And let's assume that the initial data lives here, that it is strictly positive, yeah, for the density.
What does it mean, strong solution? Functions or
Strong
distribution?
solution means sufficiently differentiable in order to have all derivatives in PDE satisfied, understood pointwisely. Yeah. So strong solution means I take PDE and I find the value in every point. Yeah. So strong solution means something like C2 for the solution, emanating from data like that.
Okay, it's written. Okay, it's
Yeah.
written.
So assume that the strong solution belongs to that class. At the moment, in this first result, we assumed it. Later on, we proved it together with my colleagues from Warsaw. Then, if it happens that my measure-valued solution, my Young measure solution, emanates from this initial data that gives rise to the to the regular solution, yeah, then the measure-valued solution stays the same as the regular solution. So what it says is that if I have initial data that generates regular solution, of course, I know I can prove that it generates also this very weak measure-valued solution, but on the interval of existence of regular solutions, these two solutions have to be the same. So my probability is exactly equal to 1 that my measure-valued solution is equal to the classical solution or regular solution, okay? So this is the so-called weak-strong existence result, yeah? If I have regular solution, and we know we have it, then the measure-valued solution is the same. And I think I'm going to stop here. I'm happy to share the slides, the rest of them. Also, the last slide, which has a list of problems or open directions that we work on right now. Unfortunately, I didn't talk about problem number 2, about passing to the limit in the offset function, but I'm happy to take some questions now. Thank you.
Okay, thank you very much. Okay, are there any questions? Please, the questions? Artur?
Yes, I have one question related again to this exponent gamma. So you mentioned that it is not appropriate for this model for traffic, but it is appropriate for modeling the movement of pedestrians. Yes, and I'm interested in the exact value of this gamma, how it is obtained, and also what is the precise value of it.
I don't know what is the precise value. Let me check if I can come back to. Let's see if we can. Okay, so everybody sees it. So this is the question.
Yes.
So what is done in this paper really is they take any positive value of gamma and they see certain things. They measure certain things. First of all, how big concentration can get. Second of all, the speed of emptying the room. And then some kind of concentration waves or propagation, speed of propagation of concentration waves. Yeah. So all of it can be linked to gamma. They are also studying in this paper limit when epsilon goes to 0. Yeah. And all these parameters that I mentioned will be linked to gamma, but also to this parameter epsilon here. Yeah? So these are two parameters that you can adjust. But none of there is no like physical experiment in that paper. Yeah, they take, I don't know, faster goes slower behavior, and they see, okay, our model can describe that qualitatively, right? Not quantitatively. There is no quantitative behavior here. Maybe they work on something, maybe they don't. I don't know. I talked with these people maybe like at the beginning of this year, and nothing more was done in that direction. But the person number 2, Rafael Bailo, in this group, he now received a position in Eindhoven, and I see in his grant description that he is working to put some machine learning component into that model. Yeah, so they are developing that model.
So, so maybe let me put my question in maybe a different terms. So, you are suggesting that there is no, how to say it, physical, some general reason for the specific choice of gamma. It is not like that. So I'm alluding to situations in physics where you have some heuristic arguments, but still they are very powerful in order to obtain some explicit exponents in some scaling laws and so on. And these are usually very important numbers which give some deeper insight into phenomena. So here it is probably not the case that there is some general argument which can be done.
You can tailor it to certain description. So this model again, right? It's something that can be derived from microscopic models. So if you like observe interactions between, let's say, 5 or 10 particles, yeah, and write ODEs for each of these particles, that exponent gamma is something that appears in these microscopic interactions. Yeah, so you can like, if you know that at the microscopic level there is some interaction, and it's again this sort of generalized follow the leader dynamics. Yeah, that you interact with one particle at the time. Yeah. So if your interaction there is prescribed by this gamma, yeah, you can coarse grain this model and obtain this macroscopically. Yeah. So this is the effect of the microscopic interaction. Yeah.
But people had done this, or
so this model, this paper here, they say it's formal. It's very formal. They did it. Yeah. They wrote the microscopic formulation for that equation. But then they said, okay, in the limit, you know, assuming propagation of chaos or whatever physicists usually assume to derive macroscopic models, they did it, yeah? But it's not a rigorous mathematical argument. What I can show, for example, is only that if I have a macroscopic system that I'm working with, right, and plug in very specific, what I call monoatomic ansatz, monoatomic solution, which means that all velocities for the microscopic model concentrate around my macroscopic velocity. Yeah, so sort of this ansatz into my macroscopic model, I can say, okay, this is a solution to microscopic model. This is something that I can prove rigorously, that I have a framework of solutions that allow me to choose this form of solution, and then automatically it has to satisfy the microscopic model. But it says basically there is no interaction. So if there is no interaction, there is no difference between micro and macro. Yeah. So that's something I can prove rigorously, but to pass to the limit from microscopic system of n agents when n goes to infinity with complex interactions, nonlinear interactions, it's a difficult thing. It's the whole mean field limit business, yeah, to prove it rigorously. And I like to prove things rigorously. Yeah. So formally, you have they say, okay, from here, and then it worked in many cases, okay, that somebody postulates the formal limit and then rigorously, I don't know, a decade later, mathematicians can prove it, yeah? And numerically, they also have simulations for particle system here and for the macroscopic system. Yeah, so for particle system that they claim is a mother of the dynamics, and macroscopic PDE system, and they agree. Yeah, so they hypothesis that this should be macroscopic, accurate macroscopic description is numerically confirmed. Yeah,
Numerically, okay.
numerically.
And still no precise form of this gamma, but only
Mm.
the
And
existing.
I don't think that they are interested. I mean, at least de Gaunt is a mathematician by training. Yeah? He did his PhD with Bardos on Boltzmann equations. He is very strong mathematically, and I think that he is interested in more or sort of analysis of system per se, like what are possible behaviors of the system. But really, in order to look for specific gamma, which I understand you're asking me about,
Yes.
there would have to be somebody in this lab who is a physicist, and none of the other authors is a physicist.
Okay, thank you.
Are there any questions from people on Zoom? Okay, it seems that not. Any questions from people on site? Okay, if not, let's thank Ewelina again.
Thank you. So I stop sharing.
The recording. How should I stop it? Alt C? Ah, yes.